Okay, today we want to talk about inverse trig functions. We are going to limit ourselves to the three basic functions, primary functions, which are sine, cosine, tangent. These are the functions that show up on your calculators. They have a so-called inverse, which depending on a style could be written either as an arc, sine, and sometimes as sine with a -1 on top of it, read as sine inverse. So this one will be arc cosine or cosine inverse, and this one will be arc tangent. And for that there is also tan inverse. On your calculator you might see either this notation or that notation, or even a third notation might show up depending on a make and a model. Now before we go into detail about these things, I'm going to do some brief review from college algebra. On general inverse functions, not talking about trig functions, but in general, what do we mean by inverse function? Well, operations that you study in mathematics typically come in pair. For example, you have addition and subtraction. You have multiplication and you have division. You have taking some number and raising it to the third power, and the opposite of that, taking cube root of some number, and so on. So operations do come in pair, and every time we create or talk about the sum function, we might ask about what is the pair of it. Let's go ahead, investigate these things a little bit more and see what is meant. Suppose I have a function, and the function's generic name for them is just f, first letter of the word function itself. So it's just a generic description, and then I give a formula for what I actually do with that function. Suppose my function is to double its input. If I want to investigate this function, I can always make a table with a column for my input and another column for the output. I can put some representative numbers. For example, if the input is 1, the output is 2. If the input is 5, the output is 10. If the input is 20, the output is 40, and so on. So usual application of a function is to go from input to the output. Sometimes you want to come back from the output back to the input. Suppose your output was 60. What do you do to 60 to get your input? Divide by 2. That operation of taking something and do something to it so that your original number is recovered, that's referred to as an inverse function. So in case my number here was something called t could be anything, how do I go back with it? Take that number, and what was your recipe? Divide by 2. Now, good style mathematics is going to use one letter for this, another letter for that. But sometimes either function is being applied to the same set of numbers. So letter x might be used here to represent any of these things, in which case you say if the x shows up here, you divide it by 2, and your inverse function is going to be x over 2. Now it comes to the notation issue. The most general notation is to use your original name, put a -1 on top of it, and give an input letter to it. Typically it's just the x. Whatever idea you had here comes here as your formula. Several things need to be paid attention to. A typical issue in mathematics, using the same notation to mean two different things and causing confusion by that. So you want to be careful about some of these problems. Careful about notation. In elementary algebra class, if a number is given to you, that a to power of -1 is a shorthand for what? It's a shorthand for 1 over a. So when a is a number, when a is a number, then putting -1 on top of it so it becomes an issue of being familiar with a field's terminology and jargon and whatever else they're doing. So here f isn't a number, it's a name of a function. Putting a -1 on top of it doesn't mean that I am doing such a thing. So even though f is as good of a letter as a is, but the reason for confusion in the mind of many students is that, well, you were telling me this when I was in 8th grade, and now all of a sudden you're telling me don't do this. Why not? What is so bad about the letter f? Well, nothing bad about any letter. It's just that what is it that that letter represent? If that letter was representing a number, that is agreed upon by everybody. But when f is name of a function, f inverse has nothing to do with 1 over f. So here your functions is to double f inverse. It means cut in half. For example, it's not 1 over 2x or anything like that. It's just opposite operation. Let's go ahead and practice some other functions. Suppose I have y is equal to a function f of x, and that is, say, 2x plus 3. We said our procedure was to make a table to investigate what is going on. So here's my x, here's 2x plus 3. So if my input is 1, this is going to be 5. If my input is, say, 6, this is going to be 15. And suppose I ask, if my output was 33, what would have been my input? 15. How do we get 15? You say 33 is your 2x plus 3. First, remove that additional 3, and then cut in half to get your 15 back. So what have we done? We have said 2x plus 3. That is your output. It's supposed to be 33. You're trying to recover x. What are the steps? You subtract your 3 first. Then you divide by 2. So if I had my output some entry t, what was my input to begin with? What should I do to get my corresponding input? You had t minus 3 divided by 2. So the opposite of double and add 3 is subtract 3 and divide by 2. Notice not only each of these functions have been converted to their pair, but the order in which you are doing is also reversed. Here you double first, then you add. Here you subtract first, then divide by 2. For simple functions, undoing this is a simple task. But if the function is complicated, the process of going back becomes really laborious and quite a challenge. It's like sometimes you eat a mystery meat in a cafeteria and wonder, what was it that turned into this thing? To do a detective work and go back and find out the origin of something is not easy at all. It's kind of if you have a glass of milk, spilling it is very easy, but collecting spilt milk is not as easy. Same way, a function given by these type of typical formulas, applying the function is easy, but going backward might not be that simple. So that is a general issue. We don't necessarily want to go into much deeper in that. We just want to say that finding inverse function might not be a simple task like what we are doing here. So when you are using a calculator, not only you pay for these, but you pay for the privilege of being able to do these. What the calculator goes through to figure this out is not just a simple addition to that. It has to go through a laborious exercise to actually perform each of these. Now, what we want to do today is to investigate our trig functions and see what is the reverse procedure for each of those. We are going to have a little bit of difficulty with respect to that. To explain that difficulty, again, I pick a problem from college algebra and try to explain the difficulty in that context. Function y equal to x squared we have all seen. Here's x squared. So for example, if I have 3 here, that's going to be 9. And if I have 5 here, it's going to be 25. The question is, suppose I give you an output here and ask you what was the input. What is the challenge you are facing here? Square root of 36, well, that is 6. But in addition to that, there is a little bit of an issue here, which is what? Yeah, not only 6 is an answer, but also negative 6 is an answer, because negative 6 squared also gives you 36, just as well as 6 does. So when you want to go back, you don't know which one to go back to. Since you don't know which one to go back to, you don't really have a function. The main claim to function is that it gives you a clear recipe to do one thing. It doesn't leave any choice to you. So the function is like an ironclad legal agreement. It doesn't leave any kind of arbitrary decision making as a part of it. It's supposed to be very clear. So what do we do? First of all, first thing we can say, well, this function doesn't have an inverse. This function simply does not have an inverse as is. Unless you're willing to do something, you cannot, inverse function, I should say. If you insist on having a function, can't have it because we don't have a recipe to tell us which one of these things to choose. Why should I choose one of them over the other one? As opposed to that case where we had no issue with it. So inverse functions don't always exist. But this is so natural, we want to use it one place or another. What is our solution? First of all, we draw the picture. So, well, let's see visually what's wrong with this thing that creates this problem. So I go ahead, say, okay, x squared, I have seen it a zillion times, so I'll be quick with that. So here's the graph of y is equal to x squared. This second column are numbers that shown up on the vertical. First column, numbers on the horizontal. So if 36 happens to be, say, here, the way to trace it back to where it came from is to draw a horizontal line and see where was this number. Wait for intersection, go back down. It should have been a 6 here that when you squared it, you got 36. But the problem is that there is also another intersection which leads you to another number, minus 6. So we get the idea that if you have a graph of a function in front of you and any horizontal line crosses the graph more than once, you are out of luck. The function does not have an inverse as it is. So let's write that down. That's called the horizontal line test. if a horizontal line crosses the graph of a function y equal to f of x at more than just one point, then that function does not have an inverse function. Let's put it in parentheses. Now, we don't want to throw the baby with the bathwater, say, okay, no, let's just go home. This can't be done. We want to find a solution. What do you do? Well, if a horizontal line is crossing the graph more than once, go do a little surgery on your graph. Remove some portions so that whatever is left will function for you. So we say here, for example, if you just take and remove this portion. So do a surgery and just take that portion off. Whatever is left is not going to offend the horizontal line test because simply you remove that. There's nothing there to have an intersection, and then you live with this. So that's going to give us the idea of a restricted function. So if you have a graph of y equal to x squared, where x was any number with this kind of a picture, you can go and talk about restricted version of this. The formula is the same, but you choose your x's so that that offending party, the fact that you had two intersections, that is gone, and people just sit down and fight over this issue. With respect to that, there is no fight. Say, okay, restrict yourself. Restriction means your x's are restricted. If your x's are restricted, what does the picture look like? In this case, it's just a half of a parabola. It starts from here and goes up. This one doesn't violate the horizontal line test because once you draw a horizontal line, you just cross once and you come here, and that is the inverse of that. That's what you do when you take square root. When you take square root, in high schools, there are sometimes teachers say something different from what I'm saying now. It's all just a matter of style and such. Don't get too offended by this thing. Square root of 36, by standard definition of any of these texts that you use, is just 6. So if you start with 36, the answer is, to square root, is 6. Of course, if you were solving x squared equal to 36, you say it has 2 roots. This is not because the square root has 2 answers. It's because you are solving that equation which has 2 roots. One of them is plus this, another one is a negative of that. The square root by itself, by convention, is just one number. Okay? Somebody else might make a different convention, but that is the convention of all of the texts that you use. Square root by itself is, if it exists, is a positive number. Okay. With all these things said, the question is, how about our trig functions? Do they have inverse functions? Let's take one of them at a time. So y is equal to sine of x. Question: does this function have an inverse? No. It violates our horizontal line test pretty bad because, well, we studied these things. The main claim to fame was that they were periodic. They have this wave going on. And if you take a horizontal line and draw it, chances are quite high that you get lots of intersections. Each of these could be a fair so if I have a numbers up here, suppose I pick a number, say 1/2. I ask, when is it that sine becomes a half? Well, there's one of the famous angles that we know right off the bat, but the problem is that there are a lot more functions, more angles with the same property. So we say x, the one that we are most familiar with is how many degrees? 30 degrees or pi 6, is that right? Let's remind ourselves of that famous triangle. 2, 1, radical 3. This was the 30-degree angle situation. Sine of that is the ratio of opposite to hypotenuse is 1/2. So the angle in the first quadrant that fits the bill is 30 degrees or pi over 6. So that is the one we are most familiar with, or 30 degrees. But who is this other guy? How many degrees is that? 150, yes. 5 pi 6. How about this guy? Who's that? It's like I have gone through one circle and then 30 degrees more. So how many degrees is this one? 390. That is, you take these answers that you know about, you add 360 to them, you get more. Like 150, you add 360 to it, you get what? 510? Yeah. What about backing up? Where is this guy? You take that, you back up by 360. What angle is that one? If you start from here, this is really a sister of minus 210. So a function like sine x offends the horizontal line test a lot worse than parabola did. What did we do with the parabola? The parabola, we said, okay, here's a parabola. You have somebody who's messing up the picture for you. You remove a portion of it, and you keep another portion. This one we keep. So here we are going to ask, what portion of this picture should I keep so that I get one answer at least every time, but I'm not going to get multiple answers. The convention is to start your surgery here. So, okay, take this portion. Come from most immediate low to most immediate high around the origin. Go from low to high. That gives you all the coverage you want. Anything else you pick is going to give you duplication. Why bother with it? Just go over this portion. So that's going to become our so-called restricted sine. So again, why are we choosing this piece? To avoid all these answers. Like here, I only have that. I don't have any other answers. Why here and why not something else? Well, that's a matter of convention, and well, these numbers are smallest numbers, nicer numbers to play with. 30 is a lot easier to work with than 150, so we stick with the small things. Question?
Yes. Would it be proper to state that as restricted to the lane?
Yes, exactly. So we're willing to learn a few other terminology here. So let's redo this thing. We have restricted sine. Start from our low, comes to our high. Our low started at what? This was minus 90 degrees, is that right? And our high was at 90 degrees. Our range is same as before. Our highs and lows are we better have those points covered. So this is a restricted sine. And as you mentioned, its domain is cut short from minus 90 degrees to 90 degrees, or if you wish, in radians. Range is not changed. It better not change because we want to have all the coverage we had before. Okay, this thing cooperates with the horizontal line test. Any horizontal line you got, just cuts it once. How about this horizontal line? Well, it wasn't cutting that one, it's not cutting this one. Simply, the function doesn't have an intersection for that. Sine never becomes more than 1. It doesn't make sense to ask a calculator or try to solve exercise yourself and try to find out when is it that sine becomes, say, 2 or 3 or something. If you ask your calculator that question, answer will be error. It just doesn't cooperate in that direction. Unless we go all the way to the end of the book, and then we have other things to tell you. But right now, this is the restricted sine. Okay. First, we know what to work on. Then we need the issue of a notation. So by now, we know if sine of, say, 30 degrees is 1/2, that means if I start at 30 degrees here, if I start at 30 degrees, if I go up, I hit 1/2. Now we want to have a name for going the same route but in reverse. I want to reverse this blue, get that black one. I need a name for it. I need a way of writing. Here are two styles. You write the word sine, you put a -1 on top of it, you put the input 1/2. Now your question is, what was the angle whose sine turned out to be 1/2? And then you write these many degrees as the answer. Or if you are working in radians and you have set your calculator to be in radian mode, it's going to show something like pi6. This is one style. There is another style that avoids this exponent at the expense of writing more. So this is one style they write, say arc sine of 1/2. That means what was the arc or what was the angle whose sine became 1/2? Again, you might come across text or maybe even some software or calculator which tries to abbreviate this. And this is 6 letters long. It's a little bit outside of convention of mathematics, where everything is tried to be 3 letters and at most 4. So sometimes they write a sine. So if you see that somewhere, be aware of it as to this is not used in our text. The ones that the text uses are these. Make sure you check your calculator, see what does your calculator say. Your calculator maybe even avoids all of these things and uses conventions such as second function to do this. Okay. So, suppose we want to graph y is equal to sine inverse of x, which we said is the same as saying arc sine of x. Graphing these functions turns out to be actually very easy. If you remember what the original function was. Original function was y is equal to sine of x. This is the inverse of that. We are going to see that there is a simple procedure to go back and forth between the two of them. Let's make a table for this guy. Remember, we are working with the restricted sign. Unfortunately, that doesn't have a notation. I wish it did, but this is a restricted sign we are working with. What are our famous angles? Let's work with those things first. 0, 30, 45, 60, 90. Stick to those. What was the sign? Sine of 0, 0, 1/2, radical 2/2, radical 3/2. This is really radical 4/2, which is just 1. Negative of these just gives you the negative of those. Well, if you are making a table for this, it means here is going to go your values. Here are going to be the angles. Really, this table is nothing other than that, except for the fact that the first column becomes second and second column becomes first. Talking about inverse function simply means swapping the two columns that you got. Input and output are going to be exchanged. Meaning what? What? 0, 0, that is easy. Let's go at this. If your x is 1/2, we are asking what was the angle whose sine was that? The answer is 30. What was the angle whose sine was -1/2? Well, it was -30. How about radical 2/2? What was the angle whose sine turned out to be radical 2/2? 45. And so on it goes. So now we need to review a little bit from college algebra to see, okay, the tables, one of them is exactly the other one with the column exchanged. That's all. But how is that going to influence the picture? To see how it influences the picture, let's go do something a lot simpler than these numbers. I ask you to plot. Plot, let me pick some numbers such as 1 and 2, and 2 and 1 on the same picture. Why am I insisting on such a look? Because like here, you have 90 and 1, here you have 1 and 90. All that has happened is that you swap the two. I pick two numbers and exchange them and check, see what kind of a connection do they have with each other. So here is, say, 1 and 2. So 1 and 2. And then, say, 2 and 1. Let's take another pair. Again, some reasonable numbers. Such as, say, 1 and 3 versus 3 and 1. What I'm after is there any kind of a transformation that I can do, like a physical movement that will go from this one to that one, or will go from this one to that one? I know that I'm just exchanging the coordinates, but is there a physical description that will do exact same thing? Well, Let's pick one other point. Suppose I had 1, 1. If I exchange the coordinates, I can come back to 1, 1. I'm right at the point I was at the beginning. So here is something that you might have seen in some of your classes. Where should I put a mirror such that the blue becomes a reflection of the green? Yeah. So, okay, if you put your mirror right on the 45-degree line, reflection of the green is going to be blue, and reflection of the blue is going to be green. What do you mean reflection? Reflection means go straight to the mirror, go equal distance to the other side. You're just getting a reflection. Here, come to the mirror, come equal distance to the other side. You come back to the second point. No, my drawing wasn't that good, but that's the idea. So what we understand is that when you want to plot these two graphs, well, you can go and do everything from scratch if you wanted to, but if you have one of these things, you can put a mirror next to it, get a reflection of it. The reflection is going to be the graph of the other one, and you're all set. You can go about the rest of the business. So here I say, suppose I had graph of sine. Here's the graph of sine. How did it look like? Something like this. For example, in degrees, you went from minus 90 to 90, restricted sine, and you went from minus 1 to 1. Let me change my mind and do this thing in degrees so that things are not going to. So here is pi over 2. Here is minus pi over 2. Now I want to put a mirror here. Here is my mirror. I take this red curve. Let me thicken it again. I take the mirror image of it. What does that mean? It means from here, go straight to the mirror, go equal distance to the other side, stop here. If you were here, go to the mirror, go equal distance to the other side, stop here. This is right on the mirror, so its reflection is itself. This one, come to the mirror, come equal distance to the other side. So let's take a mirror image of this. It's going to bend this way. So this was 1 and pi over 2 on the blue curve. 1 comes here, pi over 2 goes up here. Or minus 1 comes here, and minus pi over 2 comes down here. So the blue curve is really sine inverse of x, while the red one was the restricted sine of x. So restricted sine had a domain set of x's that we were using, like from minus pi over 2 to pi over 2, and it had a range from minus 1 to 1. Sine inverse or arc sine has these two swapped. So its domain, what is its domain now? The blue one. The domain is set of numbers on the horizontal x-axis, for which you have a recipe what to do. It's from minus 1 to 1, and its range is going to be from minus pi over 2 to pi over 2. Now, this picture turns out to be kind of tricky. If you try to draw it by itself, it's a little bit hard to follow, or your hand is not going to do the right thing. Let me show you a little trick that makes the topic more understandable and also helps you with picture itself. So question number 2 is, if I have the entire, suppose I take the whole, sorry, let me write this again. What does sine look like? Let's say. Kind of like this. It weaves around the x-axis. Now do exact same thing around the y-axis. That is, take a wave that winds around. I have to mess up my previous picture, but that's fine. Okay, so I have a wave that winds around the y-axis. This is x, this is y. So just let your hand go up and wave around the y-axis. Then comes the cutting portion of the job. You say, okay, I have my sine restricted from its low to its high. So on the vertical, I go from the leftmost point of it near the origin, and I go to the rightmost point of it. So these are the yellow portion is the restricted sine, the green one is the inverse of it. Okay, this story has to be repeated then again for each of our functions, for cosine, tangent, and actually for the secant and cosecant and cotangent. But as I said, we are going to just keep ourselves to the primary functions. So let's take a 2-minute break and we come back and continue with the other 2 functions.